We're going to be looking at problem number 28 on page 466. This is a good application problem on the sampling distribution of a sample proportion. What we have here is a population proportion of 0.3, and I think in context of the problem that means 30% of these pregnant women are living within 1 mile of a hazardous waste site. And for part A, it wants to know if you have a sample of size 10, if it would have an approximately normal distribution. Well, the check for this with population proportions is to try n times p and n times 1 minus p. And you could plug in and try to check if those are both greater than 10 or not, but it's going to be pretty obvious that 10 times 0.3 is not going to be greater than 10. Regardless of what your sample proportion is, you're going to fail to meet those conditions if you only have a sample size of 10 to begin with. 10 times any proportion is going to not be 10 for at least one of the two. So the answer for part A is that it would not be appropriate. Now for part B, they're going to a sampling distribution of a much more appropriate size. This time we're picking a sample of size 400. And clearly, if you have a size of 400, n times p would have been 400 times 0.3, which is significantly larger than 10. That comes out to be 120. And then you would also have to check 400 times the chance that they don't live near the site, 0.7. But clearly multiplying by 0.7 is going to give you an even bigger answer. In this case, 280. So in both cases, you're well over your rule of thumb of 10. So it's very safe to say that this sampling distribution is going to be approximately normally distributed. And then it wants to know what the mean and standard deviation are. The mean of your sampling distribution of your sample proportion is going to turn out to be 0.3, because the sample proportion should always average out to be the population proportion, because that is sample proportions are unbiased estimators of that population proportion. The standard deviation would be p times 1 minus p over n, like we did on the previous problems. So what you're going to have in this case is your sample proportion is 0.3, the chance of failure is 0.7, and then my n value is going to be 400, and then I'll just put that in the calculator to get a value. So that simplifies to be about 0.0229, so roughly 2% is your standard deviation of your sample proportions. So they're going to be centered at 0.3, and it'll be very typical or very usual to be as high as 32 point something or as low as 27 point something percent for an individual sample proportion. Now, for the next one, it's looking for the probability of it falling in a certain range. So I'm going to sketch a graph of this sampling distribution over here. And it's going to be centered at 0.4. And we just found out we were typically off by about 2%. So I'm going to go, my inflection points are going to be here about 42, 2 standard deviations about 44, and 3 standard deviations about 46. And then the same thing on the other side, 1, 2, 3 standard deviations spread out about 2% each. So my distribution is going to be centered here with inflection points there and there. So it's going to look something like this. It's going to be my sampling distribution. Now, once I have a sketch there, it wants to know the probability in between 0.25 and 0.35. Well, 0.35 is obviously pretty small, and 0.25 is even smaller than that. I guess it would be all the way over here, way back yonder for 0.25. But if I look at how much area I have there, it's going to be not very much, because it's practically nothing until I'm getting close right toward 0.35. I might get a little bit. So I'm going to be expecting a very small probability there. Okay, as I sketch this sampling distribution, it's going to be centered at 0.3. Since my standard deviation is about 2%, I'm going to have my inflection point at 32, 2 standard deviations about 34, 3 about 36, and then the same thing going in the other direction. So it's going to be centered at 3 with my inflection points there and there. So I'm going to be looking at a distribution that looks something like that. Oh, I didn't do a good job. Let's see if I can do a little bit better. There we go. You can probably do an even neater job of graphing these, but that gives you an idea of what it would look like. So if we're looking for the probability that it's between 0.25 and 0.35, what you will see is that is most of your distribution. So practically all of my distribution is somewhere between those two values. So I'm going to be expecting a very large value. I would say at least 90%, maybe up close to 95 or even more is going to fall in that range. Now to get the exact value, of course, what I'm going to do is I'm going to find the probability that I'm between 0.25 and 0.35 for a sample proportion. As usual, I'm going to need to convert these into z-scores. So for z-score here, I'm going to do 0.25 minus 0.3, my mean, divided by my standard deviation. And like I mentioned with sample means, it's best not to use rounded decimals, so I'm just going to write that in as 0.3 times 0.7 divided by 400. And that's going to be less than z, which is going to be less than the same thing in the denominator, but it's going to be 0.35 minus 0.3 in my numerator. So if that gives you an idea of how we're going to convert to z-score, we'll reach for a calculator to get those z-scores converted. And that was going to end up with z-scores of about negative 2.18 and positive 2.18. Now to do that with the calculator, I can go for normal CDF. And that's going to be my low bound and my high bound. Once again, when I'm in z-scores, there's no need to adjust mean and standard deviation. And what you could do to avoid having to type that in is, of course, I could do, it's okay to do second answer when you do normal CDF. And if, for example, I had that positive 1.28, since this is symmetric, I could do negative second answer and just positive second answer for my upper and lower bound, and it would give me the correct value. So you end up with an answer of about 0.9709. Once again, our rounding might be a little bit different, but that should give you a ballpark answer. That matches our graph. I said it was well over 90, possibly over 95%. Actually, looking at where our graph is, it makes even better sense because you notice we are past our second standard deviation. So I would have had 95% roughly just between those 2 points. So going a little bit further than that, I would be expecting somewhere in excess of 95% of my distribution. Now, for Part D, it says, is the probability calculated in Part C larger or smaller than would be the case if n equals 500? Well, if n equals 500, increasing the sample size is going to further decrease the variability of that sampling distribution. So instead of having a distribution like that, it says not to calculate it, but basically you can get the idea that increasing your sample size is going to pull that distribution a little closer together. So now I think what you're going to end up with is an even larger portion of your distribution is going to be between that 0.25 and 0.35 range. So your answer for Part D would be that increasing your sample size to 500 would decrease your variability, and that means your answer for Part C would be larger than the answer you would get if you would have had a sample size of 500.